In database systems, atomicity is one of the ACID transaction properties. In an atomic transaction, a series of database operations either all occur, or nothing occurs. The series of operations cannot be divided apart and executed partially from each other, which makes the series of operations indivisible, hence the name. A guarantee of atomicity prevents updates to the database occurring only partially, which can cause greater problems than rejecting the whole series outright. In other words, atomicity means indivisibility and irreducibility. As a consequence, the transaction cannot be observed to be in progress by another database client. At one moment in time, it has not yet happened, and at the next it has already occurred in whole. The etymology of the phrase originates in the classical Greek concept of a fundamental and indivisible component. See atom. Examples. An example of atomicity is ordering an airline ticket where two actions are required, payment, and a seat reservation. The potential passenger must either, both pay for and reserve a seat. Or, neither pay for nor reserve a seat. The booking system does not consider it acceptable for a customer to pay for a ticket without securing the seat, nor to reserve the seat without payment succeeding. Another example is that if one wants to transfer some amount of money from one account to another, then the user would start a procedure to do it. However, if a failure occurs, then due to atomicity, the amount will either be transferred completely or will not be even initiated. Thus atomicity protects the user from losing money due to a failed transaction. Orthogonality. Atomicity does not behave completely orthogonally with regard to the other ACID properties of the transactions. For example, isolation relies on atomicity to roll back changes in the event of isolation failures such as deadlock. Consistency also relies on rollback in the event of a consistency violation by an illegal transaction. Finally, atomicity itself relies on durability to ensure the atomicity of transactions even in the face of external failures. As a result of this, failure to detect errors and roll back the enclosing transaction may cause failures of isolation and consistency. Implementation. Typically, systems implement atomicity by providing some mechanism to indicate which transactions have started and which finished. Or by keeping a copy of the data before any changes occurred. Several file systems have developed methods for avoiding the need to keep multiple copies of data, using journaling. Databases usually implement this using some form of logging journaling to track changes. The system synchronizes the logs as necessary once the actual changes have successfully taken place. Afterwards, crash recovery simply ignores incomplete entries. Although implementations vary depending on factors such as concurrency issues, the principle of atomicity that is complete success or complete failure remain. Ultimately, any application-level implementation relies on operating system functionality. At the file system level, POSIX-compliant systems provide system calls such as open, to, and flock, to, that allow applications to atomically open or lock a file. At the process level, POSIX threads provide adequate synchronization primitives. The hardware level requires atomic operations such as test and set, fetch and add, compare and swap, or load link store conditional, together with memory barriers. Portable operating systems cannot simply block interrupts to implement synchronization, since hardware that lacks actual concurrent executions such as hyper-threading or multiprocessing is now extremely rare. In NoSQL data stores with eventual consistency, the atomicity is also weaker specified than in relational database systems, and exists only in rows. See also, atomic operation, transaction processing, long-running transaction, read-copy update. References